brought your hot chocolate with honey, boss.
Not now, Hans. I'm on the verge of a breakthrough.
But boss, it took forever to grind up those bees.
I said not now.
What are you working on, boss?
If you must know, I'm creating a henchman.
Creating a henchman, sir?
Yes, Han. Men who hench. Never heard of them before.
How are you making a person?
What's this person nonsense your puny little mind is dribbling on about? This is a robot, an automaton.
Looks kind of, fleshy.
Of course, you Nimrod. How is he supposed to go out and hench if he looks like a metal skeleton?
How did you get the skin on him exactly?
I'll tell you that later in the podcast. Now pull that lever.
Right away, boss.
Yes! Yes, it's working! Yes! It's alive!
We're at the beginning of a new wave of research. Our creative powers are being stretched. We're learning surprising things about how we sense the world around us. Exploring the mysteries of the spoken word.
Welcome to the Future Last Week, where we talk about all things awesome and futuristic. Last week, I'm your host Wyatt, and it was week 23 of 2022. In our first story today, America has reclaimed the title of having the world's most powerful supercomputer. We took this title from Japan, whose computer is about half the speed of this new one. This is the world's first computer that is capable of exaflop speeds. Now, an exaflop sounds pretty silly, so I'll kind of dig into it a little bit. A flop stands for floating point operations per second. And floating point numbers, to put it simply, are kind of a trade-off between precision and range. Essentially, capping the maximum size of a number in a computer system in order to speed up arithmetic operations and decrease storage and what have you. So when you hear about like a 32-bit processor or a 64-bit processor, that actually defines the maximum size of a number used in the system. 32 bits is 7 digits, and 46-bit is 16 digits. And that's not to say that it's the maximum size a number can be on a system, because strictly speaking, you can have, a bajillion, canillion, or whatever the heck. But what that designation means is that that's the maximum size that a number can be in any particular arithmetic operation. So when you get those really, really big numbers, that's actually just multiple numbers stacked one after another. In a 32-bit system, you can only have a 7-digit whole number or a 7-digit decimal number and everything in between. This is why we call it floating point, because the decimal point actually kind of floats around the number. If you need more precision in your math, you would use a higher bit processor, like a 64-bit, for example. Now, 64 bits actually would have a lower flop rating than a 32-bit processor, because in order to do operations for numbers that are twice the size, it's going to take twice the time. And vice versa for 32-bit, with that taking half the time of a 64-bit operation. To get back to the actual supercomputer itself, now that we've kind of explained what a flop is, an AMD Ryzen 5000 processor is rated for about 32 flops per core, and the best 5000 series has 16 cores, giving it a rating of 512 flops per processor, and that's a 64-bit processor. This new computer is rated at 1 exaflop, which is 1 with 18 zeros after it. It has 8,730,112 CPU cores using the AMD EPYC 64-core processor. That means that this computer is made out of 136,408 processors at a price of around $341 million at retail. That's not including the scaffolding or the boards or really anything else, not all the drives. So I'm sure this computer was probably at least $500 million, somewhere in that range, most likely. Now, why would you build a computer this crazy big? Well, you can use a computer with that kind of processing power for a lot of very useful things. Medicine is probably not an application you think of when you think of computing, but you can use algorithms to predict and design amino acids and special proteins in order to get desirable effects. You can make a protein that inhibits the Ebola virus, for example. And using a human mind, that would probably take a very long time and lots of trial and error, but a supercomputer can design this protein and it can just keep running simulations over and over until it gets a shape that seems to be the most effective based on what we know about the virus. Engineering, of course, is another one. Designing structures, designing products, designing spacecraft, all sorts of different stuff with that. Just making the most efficient designs possible using artificial intelligence. With this much processing power, you could probably do it in a very short period of time. Cosmology being another one. With this much computing power, you could probably simulate our entire galaxy and see how all the individual pieces interact, and you can compare that to current scientific models and see if there's anything that we're missing. And I think the final but most important use for a system this size is that you can run Cyberpunk at 60 FPS 4K resolution with ray tracing. And for $500 million, that's one hell of a steal. But that's enough about the new supercomputer. It's kind of all I had to say about it. It was just kind of a new development. I also kind of wanted to dig into what a flop was, because before doing this episode, I didn't actually know what it actually was. So I learned a little bit doing this story. Our next story kind of made me a little bit upset. And not because of the contents of the story or anything, but because the title was like super clickbaity. The title reads, "Solar cell innovation generates 1,000 times more power." Now, if you didn't read the article and you only read the headline and moved on, you would just assume, oh, that's awesome. They figured out a way to squeeze 1,000 times more power out of a standard solar panel, and so now you can power a whole house off of one tiny solar panel. Well, that's not exactly how that would go down. First, let's talk about how solar panels work to get kind of an idea of why that can't be. Solar panels work on what's called the photoelectric effect. Essentially, photons collide with a semiconducting material, and they sort of just knock the electrons off. Knocking them off isn't exactly accurate. It's more like the electrons absorb the energy from the proton and gain enough energy to break free their atoms. Now, when you have free electrons floating around, that produces voltage and generates electricity, just to keep it super, super basic. Silicon is typically the semiconductor used today. Almost every single solar panel you can buy is going to be silicon-based. It's the best material that we've found so far. Now, silicon solar panels have a maximum practical efficiency around 32%, meaning if 1,000 watts worth of sunlight hits the solar panel, we only get 320 watts out of it, and that's at absolute max efficiency, which is never going to happen. The majority of solar panels that you can get on the market for a reasonable price are 22% efficient, meaning 1,000 watts of sunlight, 220 watts of electricity. So knowing that, we have our 22% efficient solar panels. According to the headline, we can now get 1,000 times more power out of them. 1,000 times 22% is 22,000% efficiency. And that's just not possible. You can't get more energy out of the sunlight than it can actually transfer into the solar panel. That would just be free energy. Now, actually reading into the article, the title isn't exactly incorrect. It's just wildly misleading. The scientists in this article are experimenting with a new material to try and get as much electricity out of sunlight as possible, as well as decreasing manufacturing costs. What this article is about is that a chemistry that they had been experimenting with, they recently made a breakthrough and now they are getting 1,000 times more power out of it than they were before. Now, before, they were hardly getting any electricity out of it at all. With this slight change to the formula, they're now making quite a lot of electricity, enough to be comparable with a silicon solar panel, or at least that's the hope. The chemistry in question is barium titanate, as in titanium, a mixed oxide made of barium and titanium. And the significance of this, if you listen to the last episode, titanium is actually sensitive to light in a way, or at least titanium oxide is. And when you expose it to light, it has a tendency to react, and you can use that chemical energy to do all sorts of fancy stuff. In the last episode, it was splitting water into hydrogen and oxygen so that you can produce hydrogen on the cheap. In this case, it seems that it would be used to generate electricity. The advantage of this new chemistry is that there's no PN junctions. And a PN junction is essentially little transistors that are all over the material that allow it to semiconduct and kind of switch on the power on and off, and actually absorb that sunlight and turn it into useful electricity. Well, that makes the solar panel actually fairly complicated, because you got all these little switches basically all over the thing. With this new chemistry, you don't need the PN junctions, meaning a drastic reduction in manufacturing costs and a much higher durability because there's nothing to break. It's just straight material. Another really big advantage to this material, at least what they've been able to find so far, is that over 6 months of intensive testing, there was no degradation in the material at all. It produced the exact same amount of electricity as when they first started. That alone is worth the change, even if we say it was 15% efficient versus the 22% efficiency that we get out of standard consumer panels. Well, you have to replace those standard consumer panels over 20 years. Now, what would it be like if you could buy that panel and you'd never have to replace it ever? Would you take the performance hit? Probably. 15% over 22% is maybe a bit much to ask. But of course, with the decrease in manufacturing costs, the panel itself would be a lot cheaper. And even if you needed more, you could afford more. And then those ones would never die. The 1,000-fold increase in this chemistry that they're referencing is actually due to a move away from pure barium titanate. Before, what they were doing is they'd make a sheet of pure barium titanate and they would shine a laser on it, and it wasn't really doing much for them. What they changed is that now it's a bunch of stacks of very thin layers of different materials. The different materials are strontium titanate and calcium titanate. So they stack them one after another on top of each other, really, really thin. And that allowed for 1,000% increase in power. The interesting thing is that strontium titanate and calcium titanate on their own don't do anything when you shine light on them. But for some reason, when you mix them with barium titanate, which on its own doesn't really make that much electricity, somehow drastically improves the output. So they're doing research on that right now, seeing what's going on, all of the electrical interactions in there. But we could be looking at much cheaper panels in the future, much more efficient panels, perhaps, and much more durable panels that don't require special packaging. Theoretically, all you would need is just a case, a piece of glass over it, and then you just have your material inside and you have your wires hooked up to it. So, one more addition to the ever-expanding race for better solar panels, and I can't wait to see these on the market. Now to get to the story that lovely intro was all about. Now, when I read this story, if you couldn't tell, first thing I thought of was Frankenstein. The whole, it's alive thing and all that. They have put human skin, it's not just any skin, it's specifically live human skin. They've grown it over a robot finger. The skin is alive, actually alive. Now, these guys called biohybrid engineers, which is a thing now, grew it on the finger by, first they built the robot finger, and then they submerged it into a kind of big blend of collagen and human skin cells called dermal fibroblasts. The mixture settles into a base layer on the skin, or dermis, covering the finger. Then they pour liquid containing human keratinocyte. That's a fun word. Keratinocyte cells onto the finger, which then form into an outer layer, or an epidermis. After about 2 weeks, the skin covering the finger measured about a few millimeters thick, comparable to the thickness of our own skin. The skin was strong and stretchy, and the robot could heal when you cut it. Of course, it doesn't have an immune system or any kind of repair mechanisms, so what they had to do was when they cut it, they put a collagen bandage on it, and within a week it kind of fused with the skin around it, and it ended up healing itself. The biggest downside here is that you can't just grow skin over a robot and have it look exactly like a person and have it go walking in the street just yet. They have to pretty much keep the skin soaked most of the time in sugar and amino acids. So it's very rarely ever actually exposed to the air. Now, that's not to say that it wouldn't be that hard to build a robot, place the skin over it in the same manner I told you about, where they dip it, get the base layer, and then you do the final layer, and you have the robot designed with a circulatory system. Lots of little tubes going all the way around, supplying the cells with nutrients. Now, I realize that this is essentially, we're just essentially making a person at this point. It gets more and more complicated because you have skin on the outside, and now you need to supply it with nutrients, and if you want the robot to not damage its skin all the time, you're going to have to incorporate sensors or basically, a nervous system. And so as you get more and more into it, eventually you're just making a person. Now, that person probably wouldn't have to eat or anything like that, but they would have to take in nutrients of some kind in order to feed that skin. So we're not exactly going to see the Terminator anytime soon, which is probably a good thing. I'm not exactly excited for the Terminator to show up and start killing us all. But it is an interesting step in a direction. I don't know if it's a good direction or a bad direction. It's certainly a weird direction. I don't know how I feel about them growing human skin cells over a robot. But, maybe one day we could be looking at a Blade Runner type situation where you have no idea if somebody's a robot or not. And if that's the case, you could be looking at a surrogate situation, if anybody's watched that movie, where you could just transfer your consciousness into a robot that looks like a person, but effectively you live forever because you're not alive. Of course, they would have to figure out how to make it so that skin cells don't age, because skin cells age just like everything else in our body. So effectively, if you did transfer your consciousness and you only had what we currently know about biology, keeping everything together, eventually your skin would just kind of slough off and you'd be left with a metal skeleton, which would be pretty freaky. Imagine if your grandma looked like that Silver Skull Terminator from the third movie. Now, this is still very much in the lab, and they're probably not going to be doing anything with this for at least a couple years. Let's hope. But it is still kind of cool to see that they can graft human skin onto robotic parts, and so there is a potential for replacement arms, prosthetics, legs, whatever. You can, instead of having a metal hook or a plastic hand, you could have a real hand. It might not be able to respond the same way as a real human hand could, but it would certainly look like one. And I assume that people that are missing arms probably don't appreciate always being looked at for not having arms. So this could definitely be a step in the right direction, as long as you don't use it for weird Terminator stuff. And before I go ahead and end the episode, I am just going to let you guys know that I will not be making an episode for next Monday, because I'm going to be on a trip that is going to require my attention for the entire weekend, so I won't have much time to put it out. But that's all I have to say about that. If you like this episode, please consider helping the show and telling your friends about it. They get the latest news about our amazing civilization, and I get to enjoy sharing it with them. This show is available on Spotify, Apple Podcasts, Google Podcasts, or wherever you get your podcasts. I also have a YouTube channel. If that's how you like to listen, just search The Future Last Week and subscribe to the channel. If you'd like to support the podcast, stop by my Patreon and consider becoming a Patreon for some cool benefits, including a shout out in a certain tier. Visit patreon.com/TFLW. Have a good week, and I'll see you next Monday.